think we're ready to start this afternoon sessions on Marco Aldi for his second lecture. Please.
Thank you. Right, so yesterday I outlined this construction that schematically constructs the manifold and attaches this standard current algebra, the current orphan algebra, and there is a standard construction that associates with a conformal algebra of currents. So this is algebra. This is the conformal algebra, and then one can quantize by taking some kind of universal developing algebra analog in the compound category and get a sheaf of vertex algebras and this parallelogram sheaf. And then the underlying philosophy, which is not mine, but I learned from some participants of the workshop, some of the organizers, Ekström, Iwani, Hallen, and Zabzine. The idea is that one can use effectively this procedure to quantize the sigma model with target X in the Hamiltonian picture. So, more precisely, we get the quantum kinematics of the sigma model with target X, and from that one can add dynamics using Hamilton's equation. And last time I concluded outlining an example where one can, goal was to show that in a simple case where one can carry out all the computations explicitly, one sees this type of object in the traditional, perhaps more traditional Lagrangian approach to quantization of the sigma model, and that was the case of torus with basic fields that are maps from r plus 1 to x. In that case, I think it's very simple because P plus the star is the trivial bundle, and therefore one can explicitly write the current algebra through speaking of its global sections.
In your general picture, was X not a complex manifold?
So far X is just a smooth manifold. So this is generated as a module for these operators of differentiation by the time derivative of x and the sigma derivative of x, and then so all the constraints coming from the equations of motions came into place, and I said that this is a really conformal algebra with bracket v tau x, lambda v sigma x is lambda, and then everything else can be recovered using the Leibniz rule. And in fact, this is the Heisenberg conformal algebra, conformal algebra. And then, in this particular example, then chiral Legrand of X is basically all X tensor with the quantization of this current algebra. And then one can write again a little bit explicitly. Now this sees a lot, but it doesn't see the winding sectors of the theory. And to do this, you saw that one can achieve that in a natural way in the Lagrangian picture by looking at the eigenvalues of the winding momentum operators, and so we get a copy of chiral Legrand labeled by lambda for each winding lambda for each element of the fundamental group of X, where all of these are isomorphic to chiral Legrand on X. They're all isomorphic copies, but this whole sum has an interesting structure. And so, if you remember yesterday, I mentioned the fact that chiral Legrand can be thought of as a quantization of functions on the loop space, and each piece here is a quantization of each disconnected component of the loop space, each component coming from a different topological type of how the string winds around X. Okay, and now this I can write in a different way as global section of the dual torus, using Fourier transform basically to identify function on the dual torus with winding modes with the lattice that defines X, tensor OX, tensor is Berkeley's algebra of currents. Okay, so this was what we did yesterday in a slightly different notation, and that was arriving at this Hamiltonian picture, but through the Lagrangian formulas. Now, one would like to know if it's possible to get the same answer by instead working purely in the Hamiltonian picture from the outside, without ever introducing the Lagrangians. Only in the end one can choose the Hamiltonian and study the evolution of these loops. This can be done. One way at least to do it is using the double field theory of Hall. The torus is the prototypical example. So the idea is to make T-duality manifest by replacing essentially the cotangent bundle of the loop space of X, which breaks up into the connected components that correspond to elements in the fundamental group of X, to replace it with the loop space of the product of X cross the dual torus, which this is called the double torus. To be more precise, what this amounts to is to introduce a new field called x star in addition to x, which was the coordinate on x, such that the time derivative of x that we have here correspond to the space derivative of this new field x star. And then you see that even in the notation, time no longer appears at this level. And I can just study loops in this bigger space of twice the dimension. So notice that.
Sorry, but you consider this condition as a constraint in the theory?
Yes.
So as a constraint that satisfies some algebra?
Right. So basically, all the most of the modes of this new field are constrained to be the same as the old ones, but there is a new zero mode, which I interpret as the coordinate on the dual
So
torus.
if you quantize the theory, you have to take into account this.
That's right. That's right. So yes, this is essentially the remark that I was just going to make. That an important point is that, which you may or may not like, that is that in this picture, momentum is quantized. Momentum, the zero mode momentum is quantized at classical level. So this is maybe a little bit counterintuitive. So here one does it, but on the other hand, one gets manifest duality, so there is a little bit of a trade-off. Alright, so how does one recover this object here in this picture? This is actually rather natural, because I can think of the lattice vertex algebra that I constructed there. So this taking sections, I can think it as, since these bundles are all neutral and everything, I can think it as pushing forward the sheaf of functions on the double torus and tensor with this vertex algebra of currents on T plus T star, which in this picture is naturally identified with the tangent space to the double torus. And the projection on what is just the obvious maps. So this I have projection onto the second factor and projection on the first factor, and then the project goes to a point. And similarly, I can repeat the same story for the dual torus, and this now is the projection onto the second torus, push forward of this very same thing. Which therefore is the same as the composition of the push forward in the x direction with the pull back in the x direction of the lattice algebra of x. So this is realizing the same object as we had before, purely in this Hamiltonian perspective. I never had to introduce any Lagrangian or anything, and it's in fact well, I worked here with vertex algebra, but it's clear that I can do the same thing at the classical level and get the same story for quantum vertex algebra. For example, by taking associated gradient places. So remarks. One can get semi-classical units. Two, global sections of this lattice vertex algebra is nothing but the usual lattice vertex algebra for the lattice lambda plus lambda dual with respect to the tautological pair. Well, one question. So, does this work for other current algebroids? Right. So here I use my current sphere. I put them back. I push them forward. Can do this for other current algebroids. I haven't thought about it, but it's an extra question. One point is to compare with a recent paper of Malikov and Sheckman on chiral William Chi transform. We work in the setting of abelian varieties, but this is kind of a real version. Another remark is that we get a shiftified picture that was not available before. So without the double field theory picture, so this is a nice sheaf on x cross x dual, and before I couldn't get such a nice picture because I was constrained by thinking in terms of the disconnected components of the loop space of X, and it's not so clear how to work with those. And once you have this picture, then at this point it's easy to include dynamics in the picture. So we can pick here, for example, a generalized metric on X and use it to construct a Hamiltonian element of the vertex algebra, which is 1/2 normal order ij of dxi dxj plus 1/2 times dx inverse j of dxi star dxj star. Again, not regular product. So this is the matrix on X. Then apply duality, meaning this relation between the lattice algebra on X and on X bar, which is essentially just a change of coordinates upstairs, and we get a dual Hamiltonian, which is associated with the dual generalized matrix as constructed in the standard way, and therefore one can apply the Hamilton's equation and get the equivalence between these models, these quantum models at the dynamical level. So you get isomorphic quantum dynamics. Okay, and then one more remark. Then you can pick, and this I'll say more about it in the last lecture, pick an isotropic decomposition L plus L dual of the complexification of T plus T star, and then one gets a generalized C structure, and this they need to n equals to a copy of the n equals to 2 superconformal algebra acting on the lattice algebra, and again, as before, one can match these structures under TDR. Alright, so.
Sorry, questa persona.
Yeah.
I'm a little bit confused. But the Hamiltonian that you have written, X star, is the T-dual coordinate of X, yes? So that Hamiltonian should be T-dual invariant.
So remember, I'm writing like this. So here I only see the space derivatives of this new field. So this means that I could rewrite it using the time derivatives of X. Right? So if, I could interpret it as the standard Hamiltonian that you would associate with this generalized metric on the torus. If you didn't know anything about the double field picture. Okay? But written in this way, yes, then it makes it clear how to go from X to X star. So, so the idea is that there is only one object, which is global sections of this sheet, and this can be interpreted in two ways: as global section of the theory on X and global sections of the theory on X dual. And then in which way you interpret it is kind of up to you. But yeah. Any other question? Okay, so this it's a nice story. I find it aesthetically pleasant, but of course it's something that is very well known. There are many ways to get the same results, so that in a sense it's not very exciting. But it's a good testing ground. So let's now look at something that it's not so easy. Just when I started to think about this, I asked around, nobody had any idea how to do this. So let's see how we can to use this approach, whether you like it or not, whether you think it makes physical sense or not. But let's try to get something new and see what we get if that is interesting. So let's now specialize to dimension 3. So x is R3 over Z3. And I'm going to pick H. This is not very important, but it's the simplest non-trivial case. A 3-4 on X. Then, using this information, I can twist the T plus C star. So this is H twisted. And basically, you add an H term, you contract the vector fields in the bracket with H, and you add this extra term to the old current bracket. And then it's been speculated the sigma model with target this twisted torus should be T-dual to the sigma model with target n, where n is the Heisenberg manifold which is the quotient of the three-dimensional Heisenberg group by its integer co-compact subgroup. Heisenberg here is the group of 3 by 3 matrices that have one element diagonal, 0 below, with entries from any array that you like. Okay. So now, so this statement appeared many times in the literature. Some mathematicians, in particular Matai and his collaborators, they had a statement like this, but only at the level of 0 modes. They were able to match somehow the functions in here with the functions here in some sense. But even though this was argued in several places where I wasn't aware of any rigorous calculation in any possible sense of the word. Notice that, again, we are not far from the previous model, from the torus. X and n are both parallelizable. So it's easy to see that sections of the current algebra associated with the twisted torus is isomorphic to global sections of the current algebra associated with T plus C star of the Heisenberg manifold. They're both isomorphic. I'll say in a second what they're isomorphic. So once again, to proceed, it's useful to employ this double field theory picture. This was also this particular example was also addressed in the double field theory literature. What should be the analog of X cross X dual that we had before? It should be the following. So first, let G be the free two-step important Lie group of dimension 6. So this is generalization of the Heisenberg Lie group, which is the free two-step important Lie group of dimension 3. Then take the quotient of its real point by the integer ones and call this y. So this is sometimes called a double two-step torus. Okay, so then at the level of currents, it's easy to see what is going on. So we have that sections of t plus t star of x twisted by h are, as I said, isomorphic to sections of Tn plus t star of n, and they're both isomorphic to the Lie algebra of G, so this six-dimensional important Lie algebra, which now we can think, since this is in manifolds again parallelizable, we can think of as sections of the tangent bundle of Y, which happens to be trivial. So this is in analogy with the picture for the torus, where we had that T plus the star of the torus, X could be identified with the tangent bundle of this double torus, X cross X dual. Okay, so then we would like to try something like we did before, to construct some sheaf upstairs on Y that then projects to X and to the torus, to the torus and to the Lie manifold, and give us the theory that we would like. But there are some issues in trying to do this. First of all, it's not clear how to deal with non-commutative windings of the manifold. So this is a global quotient, so the fundamental group of the Lie manifold is just the Heisenberg group with integer entries. This is a non-commutative group, so the connected components of the free loop space should be the conjugacy classes of this group. So phi 0 of the loop space of n, and therefore the cotangent bundle of the loop space of n, for example, and this is the conjugacy classes of phi 1 of n, which as a set, it's just a set, it's a set of conjugacy classes. It doesn't have any group structure that we can use to relate functions on different connected components of the loop space, which is what happened in the case of the torus. I didn't say much about that, but when you actually have to decide how to take the bracket of a function, say it sits on one connected component of the torus and the function sits on the other connected component of the torus, you're really using the group structure of the fundamental group. So, in particular, how to relate functions on distinct, supported on distinct connected components. It's a priori not clear, at least to me, and I formed a research that I was able to do, literary research. I wasn't able to find any, I wasn't able to find much about sigma model with target a space that has non-commutative fundamental group. And the another issue is that how should I interpret how to interpret functions on disconnected components, on connected components of the loop space of X when H is non-zero. So this it's there is at least a path here because well, you can think that H is a tree form, so you can think it of coming from a two form on the loop space. So you can think that you have that's the first chain class of some line bundle on the loop space, and this specializes to line bundles of different curvature on each connected component, and you can try to use that information to find out how to quantize. But again, it's not clear how to relate functions on different connected.
Sorry, just to ask, if you have a torus, normal torus, and you have H, you cannot have normal winding. So what's this? I mean, what's the situation for winding?
No, so I'm just looking at. Remember, for me, windings are really just topological sectors, the connected component of the loop space. So, as such, the fact that we have H there doesn't.
No, but for physicists, winding, for example, it's a solution which is linear sigma, right?
No, I understand.
Once I have a H flux, I will have a problem with this because I will get conditions that my winding time H is equal to 0.
Well,
so formally, I shouldn't have a winding.
That's why the story is interesting. But if you want to, so you are given the cotangent bundle of this loop space, and as such you want to quantize it, then you agree that you have to look at all the disconnected components, right? You're just given.
No, right, but I'm trying just to think as a solution of classical equation of motions.
Exactly,
I cannot really, if I have a H, I cannot think, I can not.
I don't want to interrupt too much, but maybe at the end we can discuss that more. How you would look at that physically.
The equations of motions are not nice, so that's not good. All right, so the idea is to combine double field theory with the Hamiltonian picture. And try to do something like we did in the case of the plane torus with no H. And so we want to look at this shift, which is functions on this double twisted torus here, tensor the currents, which, as I said, are not particularly interesting or hard to do. So what it turns out is that we get something strange, which is a vertex algebra like object, and I'll say later what I mean by that. But so this, to me, is a good reason why there wasn't much work done on this model while taking account all the windings and all the modes, because what you get is something that, as far as I know, doesn't have a name. So it looks like a vertex algebra, but you cannot use the usual formalism to describe. And then, okay, suppose that you have this, then you can get the analog of the lattice for x as a push forward with respect to x of this gadget here. And similarly, an analog of the lattice algebra for the Heisenberg manifold by pushing forward the same guy. So the remark is that once we do this, we get full, meaning all windings and all modes, Fourier modes, quantization of the kinematics of, once again let me emphasize that, of the sigma model on the twisted torus and on the near manifold at the same time. And again, this is naturally invariant under the suitable twisted version of the duality, and it checks with everything that we already knew. So if I look at no windings at all on one piece, then I just get chiral Laurent, and same if I do it on the other side. But notice that I cannot just do that. I cannot just look at the chiral Laurent and be happy with this, because some of the winding modes are going to get exchanged by momentum modes on the other side. So if I get pure chiral Laurent on the one side, I have to at least include some of the windings on the other side. In particular, everything works fine if I just restrict to 2 windings instead of 3. Then I actually get the honest vertex algebra. But I'm interested in seeing and tell you something about this this new picture that arises. So, what goes wrong? Yeah.
Where do you see that you're only equalizing one circle and not?
Oh, just this is just the way the construction goes. So if you fiber y over x and over n, you see that it's only one dimensional fiber that the difference between the fibers. What goes wrong? Well, so remember, I have to introduce the basic fields, which are multivalued, but the basic building blocks are the xi, the coordinates on x, and the xi and the xi star. So these are the coordinates on x, which is the torus, the base of this vibration, and then the xi star, which are coordinates on the fibers of the T3 vibration the double twisted torus with base x. So the derivatives of these fields were already accounted for in the non-doubled picture, but now I'm introducing these zero modes, which I'm thinking of as coordinates. And so, well, you work out the OPs, and you see that if you look at the OPs between some of the x coordinates and some of the x star coordinates, you don't get anything different than what you get for the double torus without any twisting. And this is just a logarithm which is multi-valued, but you can cure by looking at vertex operators by taking the normal order, the normal ordering of e to the normal ordering of xi z, and same for the xi stars. Okay, so this is not so bad, but the real, so these are actual, the rho is a rational function, so you get vertex algebra if you just look at this. But the real problem comes when you take OPs of two of the star coordinates, and this looks less pleasant. So you get, this is the winding operator. But then the type of singularity that you get is complicated, but in particular there is a piece which is the Rogers dilogarithm. Which is a complicated transcendental function, and there is no hope of making it nicer, getting rational functions as OPs by exponentiating, for example.
Can you remind what's the difference between this L and Li2?
Yes, well, I'm going to write it in a second. So what is this Rogers logarithm? So Lx is a function of one variable. So this is the sum for n goes from 1 to infinity of x squared over n squared plus 1/2 log x log of 1 minus x. And this is what is called the Euler dilogarithm Li2. So this satisfies a bunch of interesting identities, such as L of z plus L of 1 minus z is equal to L of 1, which is also the Riemann-Zeta function of Li2 by square over 6, and Lz plus L of 1 over z is equal to 2L1. These are easy to prove. Slightly harder is, and first sight seemingly complicated, is Abel's pentagonal identity. Which is a two-variable identity which reads Lx plus Ly is equal to Lxy, like for the logarithm, but then there is a correction term, two correction terms, which is Lx minus xy over 1 minus xy plus Ly minus xy, 1 minus xy. So the cleanest way to describe what's going on is to use this OP calculations to compute the so-called kinematic 4-point function. I haven't introduced time yet, so there's no time evolution here. I'm going but I can still take products of operators acting on my Hilbert space and then pair them together. So let me write it and I'll explain. Z1 of alpha 2, Z2 of alpha 3, 0. So this means that I'm starting with my vacuum. I apply this operator here where O alpha I Zi is a shorthand for e to the normally ordered product of x of alpha I star of Zi. Right, so these are the operators that correspond to the windings. So the alpha i's are my winding sectors. They are in the fundamental group of the torus, which is the base of the double torus. Okay. So I can start with the vacuum, apply this operator, apply this operator, apply this operator, and then pair them together and see what happens. So I don't need to have time to do this. I just need the Hilbert space and some operators to activate them. So what turns out is that this kinematic 4-point function is equal to e to the h paired with alpha 1, alpha 2, alpha 3 times the Rogers logarithm of z2 over z1. So which I interpret as an expansion in the region where z1 is an absolute value greater than z2. Okay. Now, one interesting feature about this, besides again making it clear that we are no longer dealing with a vertex algebra, there is no hope of getting a vertex algebra because the corresponding object for a vertex algebra, for example, the lattice vertex algebra would be a rational function. This is very far from that. Now, a pleasant feature about the Rogers logarithm is the following. So let delta be the hyperbolic ideal tetrahedron with vertices Z1, Z2, Z3, Z4 in the boundary. That's what it means to be ideal, because the vertices are in the boundary of three-dimensional hyperbolic space, which is which can be identified with the CP1. Then the volume of this tetrahedron in the standard matrix of the hyperbolic space is given by the imaginary part of the Rogers logarithm of the cross ratio of these 4 points. And this is nice because we get a geometric interpretation of the pentagonal identity. So now you have 5 points, and I'm going to draw a Indian picture because I already had troubles with that. I didn't want to try a hyperbolic picture, but you get 5 points. And you connect them into 2 tetrahedra. These are hyperbolic tetrahedra, so each they have their volume, and which is accounted for, say, the left-hand side of the pentagonal identity. And then to get the right hand side, you can decompose the same polyhedra in a different way. You can connect these two vertices, for example, and to stay long enough in the picture, you convince yourself that this means that you decompose the tetrahedron in this polyhedron into now 3 tetrahedra, whose volume is computed by the right hand side of the pentagonal identity. Okay? So it's pleasant geometric interpretation. And moreover, we get now going back to this structure that we have, we get a factorization result. For kinematic 5-point functions. So we can now write a 5-point function. This is C4 to 0, so for simplicity, then this is going to be a product of a bunch of 4-point functions. It doesn't matter exactly what they are, but let me just write the formula to convince you that it's very explicit. To actually derive this identity in the paper with Helwani, which this is when we found out this, we actually used the pentagonal identity, or currently we can think in terms of the composition of hyperbolic polyhedra. And now, okay, maybe last 2 remarks. First remark is actually a question. So why is the 3-dimensional hyperbolic geometry emerging from this picture? So after all, we started with a 2-dimensional theory. That's what all we wanted to study. We never tried to look for anything hyperbolic, but then you just compute these kinematic 4-point functions, and you get the dilogarithm, and it turns out that the factorization structure to go from 5-point function to 4-point functions is intimately related to the way one decomposes hyperbolic polyhedra into hyperbolic tetrahedra. And so it's natural to ask if maybe there is a reason why 3-dimensional hyperbolic geometry is appearing. So that, I heard a few possible ideas, but as far as I know, nothing precise of why this should be the case. Now, should stop here?
2 minutes.
2 minutes, okay. Okay, so, so last remark. Being honest, vertex algebras, such as the lattice vertex algebra, these endpoint functions you expected to be rational. Rational functions in the ZIs, and if you actually try to compute them using the Hilbert space structure of operators that is built in the definition of vertex algebra, you have to decide what operators you're going to apply first, and what contractions to do, and this corresponds to expanding the same function on the modular space of points on CPU1 in different regions, so depending on, say, C1 is less than Z2, is less than Z3 in absolute value. So get different expansions of the same function on the modular space of endpoints in different patches. For example, where Z1 is absolute value greater than Z2 and so on. And you can prove that knowing this factorization structure is actually equivalent to the definition of vertex structure. So now what do we get here instead? And with this I'll close for today. So here what we get is what it seems that the structure that we have is that these are no longer functions, but there are sections of line bundles, section of a line bundle on the moduli space of points, of distinct points on CPU1. And if you actually compute it again, you get different expansions in various patches as before, but might require interesting transition functions. On intersections of these patches to identify them. So this seems the emergent structure that we get. Fortunately, this is the only example of this such structure that I know of, so I don't think this is enough for maximization, but hopefully more examples will be worked out in the future. I'll stop here.
Questions? If there are no more questions, thank the speaker again.